Hi, Mr. Burke. I'm here to reassess standard 6.1 and 6.2, namely that A, I can calculate the energy of a particle at any speed, including rest energy and kinetic energy. That B, I can calculate the work done by constant or non-constant forces, and that I can calculate the dot product of two vectors. I picked chapter 6, problem 41, and I will show you what I did. So to start off with, the question was originally a question that didn't ask you, that first asked you what steps you needed to do. I simply went ahead and solved it. Just jump into it. So the first step I did was that I established some fundamental principles, like including conservation of energy. I knew that the change in energy was going to be equal to the work, and that our update form of the conservation of energy conservation principle was that EF was equal to EI plus work. Next, I established my system and certain things within my system. So I knew that my system was going to be my electron. My types of energy, I was just going to have K. My types of work was just going to be Fe. My initial state was when the electron was moving 0.91 C. My final state was after the electron had gone 2 meters. And then finally, just definition work, that the kinetic energy was equal to gamma times mc squared minus mc squared. So E total minus kinetic energy, not minus rest energy, sorry. That E rest energy, as stated, was mc squared, and that E total was, as stated, gamma mc squared. Next, with these terms, what I did is I went in, I started substituting my terms because I knew that velocity was very close to c. I knew that I could not use the approximation for k, which is 1/2 mv squared. So instead, I took this equation and I wrote it out using the variables that I established, saying that k. Well, also I knew that work was equal to a force over a distance. So my work done by the accelerator was going to be Fe times the distance, which was 2 meters. Okay, so taking the variables that I established, I turned this equation into the final kinetic energy would be equal to the initial kinetic energy plus the work done by the electric force. What happened then was a series of algebra where I essentially isolated delta gamma, and seeing delta gamma, I considered delta gamma to be too complicated and messy to really want to play with. So instead, I simply solved for delta gamma, and then went back in and solved for VF over C within delta gamma. Yes, so I solved for delta gamma after some algebraic manipulation until I got to delta gamma by itself. And then I solved for VF over C within delta gamma. And this took me a bit because the first couple times I kept getting answers which I knew couldn't really be accurate due to my use of glow script. So it took me, I think, 3 or 4 tries. My first one I got not a number because of a misplaced negative. My second I got an answer which I knew was less than the initial speed, so I knew that couldn't be true. And finally, my third try was A, slower than the speed of light, and B, actually quite close to the speed of light. So I knew that this was probably my most likely answer. Actually, no. So in summary, once I got my answer of this final speed of the electron, I went back and I realized that I only really needed to do A and B, namely that I needed to calculate the initial and final total particle energy, and that later I had to do enough that I had to calculate the net work and use the final energy to find the final speed. I neither needed to know the time, nor did I need to know the need to use the approximation for K. Finally, I did a little extension. What if Fe was in finally I did an extension. What if dr was in a more than one component direction? So I could use my dot product skills. So where the magnitude of Fe was still 2, a possible direction could be √3 in the x direction and 1 in the y direction. So I'm going to use the dot product. W would be equal to magnitude of Fe times the magnitude of delta r times cosine 45. And I got an answer. Thank you for listening. Have a good evening.